Welcome. In this video lecture, we're going to talk about applying the differential control volume approach to deriving the velocity profile in a Couette flow. So let me just first start by defining what a Couette flow looks like. You've seen this in previous lectures, but we're going to just start over here. A Couette flow, first of all, it's spelled like this, C-O-U-E-T-T-E. It's named after the scientist who first investigated this flow and derived what the velocity profile looked like. But basically it consists of two infinitely long parallel plates. Okay, so they're separated by some distance. We're going to call it H, capital H. Let's put a coordinate system on there just so we know what directions we're working with. We'll put X at the bottom, Y at the top, or I'm sorry, X going horizontally, Y going vertically. And we're going to say there is no pressure gradient, so we're going to define what this system looks like. So we're going to say there's no pressure gradient in the x direction. What that means is dp dx is 0. There is no variation in the pressure in the x direction. We're going to say that the fluid we're dealing with is incompressible. We're going to say we're dealing with a steady flow, so steady state. I'm going to say that the flow is also fully developed in the x direction. What that means is that the velocity profile does not change as we move in the x direction. There's no variation in what the velocity looks like as we move in the x direction. In other words, whatever the velocity profile looks like here, it's the same velocity profile here, same velocity profile here, and so on. So there's no variation in the velocity profile that way. We're going to say also that the flow is planar. What that means mathematically is that there is no variation in the z direction, which is in and out of the page. So the d dz of whatever is 0 in and out of the page. And in addition, so that means that the velocity in the z direction is also at most a constant. We'll just say it's 0 here. Basically, there's no flow in and out of the page, and there's no variation in and out of the page. All right, and I think that's all the assumptions we'll make at the moment. We may make some more a bit later, but I'll just write those down here. So this is really our definition of a Couette flow. We're just setting up the system that we're interested in studying. The other thing I should mention is the way that we're making the fluid move in this particular system is we're moving a boundary. So I'm going to, for this particular case, I'm going to set the bottom boundary as being fixed, but I'm going to move the top boundary at velocity capital U. And so via the no slip condition, we know that the fluid adjacent to the top boundary is going to move at velocity u, and the fluid at the bottom here is going to be have 0 speed. That's just a boundary condition. Our goal here again is to define what the velocity profile looks like in between, and we're going to use this differential approach to find that. As I mentioned just a moment ago, we can relax some of these assumptions. Like we can modify the boundary conditions. We could deal with an unsteady situation. We could include some sort of pressure gradient and such, but for this particular case, we're going to just keep all these assumptions. We won't relax them. Okay, so the first thing we're going to do is just apply conservation of mass to a very small control volume of fluid. So let me just pick a little control volume here. Let me draw it in green. Here's our little control volume. It's very small. It's differentially small. I'm going to zoom in on it so it's a little easier to see. So here's our control volume. Like I said, it's differentially small, so that means this distance is dx, this vertical distance is dy, and in and out of the page, it's a distance dz. And what we're going to do is apply conservation of mass and the linear momentum equation to that control volume. And specifically, it's really the x direction I'm interested in. But let's go ahead and apply conservation of mass first. Let me write out what conservation of mass looks like. I'll just write it over here. So here's my form of conservation of mass. Start with the basic equation. And I'm going to go ahead and simplify or write out what each of these terms is. So this first term is the time rate of change. So here's the time rate of change of mass inside my control volume, right? So what we're going to do is, well, first of all, we're going to say that the density everywhere is rho because we said it was incompressible. So the density of the fluid in here is rho. So that's a constant. That doesn't change with time. And then the volume doesn't change with time either because I'm using a fixed control volume. This little control volume here is just fixed in space. It's not deforming, it's not moving or accelerating or anything like that. So neither the density or the volume is changing with time. So that time derivative just comes out to be 0. So we don't have to worry about that. Okay. The next term is the mass flow rate term, right? So that's the mass flow rate going out and into the control volume. So here, what I'm going to do is I'm going to say that the velocity, let me just say the x velocity right at the center is ux, and the y velocity is uy, let's say. We'll also say that the z velocity is 0 because we said the flow was planar, so that we don't have to worry about that. But right at the center of that control volume, we're just saying that the velocity components are ux and uy. I don't know what those are at the moment. I'm going to try, that's what I'm trying to figure out, is what those velocity components actually look like. But for the moment, let's just say it's ux and uy at the center. And then what I'm going to do is I'm going to write down what the velocity is in the x direction as I move that direction some small distance. Okay, and as I go from the center to the side wall here, I'm moving a distance of 1/2 dx, right? It's just half of the dx here. And I'll write down what the x velocity is over on that side. So the way we write that is it'll be ux, that's the velocity I start with here. And then I'm going to add in how much the x velocity changes as I move in the x direction. So this is just the change in the x velocity as I'm moving in the x direction, multiplied by how far I've moved to go from the center to the side here. And that distance is dx over 2, right? Because I've moved from the center to that wall, so I've only moved 1/2 dx. So this is the velocity I start with in the center. This is how the velocity changes as I move in the x direction to get to that side wall. And then this is how far I've moved. Okay, so this is like my dux. It's just how much the x velocity has changed over that small distance. We can do the same thing over on the left-hand side. So to find the velocity there, I'll say it's ux is what I start with at the center. Right, I've started at the center and now I'm moving in the x direction that way. So I'm going to add in how my x velocity changes in the x direction and then multiply it by how far I've moved to go from the center to the left-hand side. So that distance is minus dx over 2. Right? And then let me do the y velocity as well while we're at it. So let me start at the top. The velocity there is going to be u sub y. That's the velocity in the y direction as I start from here. And now I'm moving in the y direction to go from the middle to the top. So it's how the y velocity changes with respect to y. And then I've moved a distance of dy over 2 to get from the middle to the top. I'm moving in the y direction. And I can do the same thing on the bottom. The velocity I start with, it's the y velocity I care about here. And then how the y velocity changes with respect to y. And to go from the middle to the bottom, I go a distance of minus dy over 2. Okay. In the z direction, I'm not going to worry about because I've said that the flow is planar, so we don't have any z component. But you can do the same idea in the z direction if you wished. Okay. So now let me evaluate my mass flow rate term. Keeping in mind that the density is a constant because we said the flow is incompressible, so I don't have to worry about any variation in the density. The UREL velocity, that's the velocity of the fluid minus the velocity of the surface, but the surface is fixed. I said this was a fixed control volume, so I don't have to worry about that. So I only have to worry about the velocities coming in and out here. And then I multiply it by the area of each face. So here, the area is going to be dy times dz, and the area here would be like dx times dz, right? So when I expand this term out, let me do it on the left-hand side first. I'm going to get, let me write it out and then I'll explain it. It's going to take a little time to write out. There's just a lot of things to write. I'm going to write the whole expression, and then I'll explain everything in just a moment. So a couple more items here. Last line. Okay, so what I've done here is I've just evaluated the mass flow rate term in conservation of mass at these 4 walls. Okay. On the left-hand side, here we have the density right there, and then we multiply it by the velocity at that wall, which is this velocity, so that's this term here, and then we're multiplying it by the area that the velocity goes through, so that's dy times dz. And when I do this dot product here, you'll see that I end up with a negative, and that's because the velocity is pointing that way, but the outward pointing normal vector for the area is pointing in the opposite direction. So when I do this dot product, I get the negative. Okay, so that's where that negative comes from. This term is on the right-hand side, so here's the u velocity there in the x direction, and then the area is again dy times dz, and then the outward pointing normal vector for the area is in the same direction as the velocity, so that's why I have a positive. And then I can do the same thing at the bottom here. So again, here's the density at the bottom. This is the velocity at the bottom. Then we have the area, which is going to be dx times dz. That's right there. And then when I do the dot product, again, the outward pointing normal is in the opposite direction of the velocity, so that's why I get the negative. And then this last term is on the top. So here's the velocity at the top, there's the area, and when I do the dot product with the normal vector for the area and the velocity, they're in the same direction, so that gives me a positive. Okay, so a little bit of bookkeeping here, but it's not too bad. It's just the same conservation of mass we've dealt with in other lectures. But now when I look at this expression, you'll see, it's getting cut off a little bit here, but you'll see that there's some terms that cancel out. First of all, you'll see this ux will cancel with that ux. This uy will cancel with that ui. And then this dux dx term, you'll see there's a minus and a minus, so that makes it positive. And then that'll add together with this dux term. And the same sort of thing with the duy dy term. This minus and a minus will add together with this one. So let me go ahead and expand that. So if I write this out, oops, let's actually get the marker here. So this is going to be a rho dux dx times dx dy, let me fix that, dx times dy times dz. And then we're going to have the same sort of thing in the y direction. So we have that. When you, basically all I've done is just done the algebra to simplify that, and we get that expression. And then what I'll do is just plug it back into conservation of mass. So you can see the time rate of change of mass in the control volume is 0, so that this term is 0. And then this term is now this, and so that whole thing is equal to 0 here. So I'm just going to substitute and simplify. There's a rho in each velocity gradient term, so I'll pull it outside the parentheses here, and then we have a dx, dy, dz, and all of those terms as well. So that's 0. So again, all I've done is I've taken this expression and I plugged it in up there, set it equal to 0. And I just, along the way, I just pulled the rho out here, and then the dx, dy, dz terms here. Okay, so hopefully you follow that. In general, the density is not going to be 0. Same with the volume, it's not going to be 0. So what we're going to be left with is dux dx plus duy dy will be 0. So this is what we get from conservation of mass. We can simplify this a little bit further with our assumptions. If you recall, back up here, we said that we were dealing with a fully developed flow in the x direction. That means that the velocity components don't change in the x direction. So what that means is that this term is 0, just because it's fully developed in x direction. So then what that means is duy dy is equal to 0. That just means that the uy velocity doesn't vary in the x direction, or I'm sorry, in the y direction, right? So it's not a function of y. Well, if you think about it for a moment, in general, let me just write it over here. So we had uy, just in general, could be a function of time and position, right? Just in general. It's the most general way that the y component of the velocity could change. But we just found from conservation of mass, it can't change in the y direction. So it's certainly not going to be a function of y. But then when you go back up to our assumptions here, we said that we were dealing with a steady state. So that steady state just means that there's no variation with respect to t, right? Time variations with respect to t are 0. So that means it's not going to be a function of time. We also said that it's a planar flow, so there's no variation with respect to z. So it's not a function of z either. And then we also said it was fully developed in the x direction. So that means it's not a function of x either. So at best, the uy velocity is a constant. It doesn't vary with anything. So at most, it could be just a constant. But we can see pretty quickly if we have a constant y velocity up here, the y velocity at these walls has to be 0, right? Because you can't have flow penetrating the walls. So we know the y velocity at the walls is 0, but since the y velocity is constant, it means it's got to be a 0 velocity everywhere, right? So since the y velocity at y is equal to 0 and y is equal to h is 0, that means that uy is 0 everywhere. So that's what we get from conservation of mass, along with our assumptions and knowing something about the boundary conditions. Now, you probably could have just figured this out pretty quickly without having to go through all the math, and that's okay. You could have written it down as another one of our assumptions up here that the flow is in layers. It's just all horizontal. Then that'd be okay too. But I just wanted to show you that you could actually prove it using some of our other assumptions up here. Okay, so now we know that there is no component in the y direction. And that we got from conservation of mass. Let's go ahead and apply linear momentum to the same control volume. I'm going to do that down here. I'm going to redraw the picture to give us a little more space. I don't have to flip the page over and over again. So again, we're saying that now that the velocity in the middle is ux, there's no y component, there's no uz component. And since we said that the flow was fully developed in the x direction, that means the velocity over here is also ux, and the velocity over here is ux. Because, just again, going back up here, we said that there is no change in the velocity in the x direction because it's fully developed. So these terms here are 0, so it's just ux everywhere. Let's go ahead and we're going to write out the linear momentum equation. So let me write that here. And then specifically, I'm going to write out linear momentum in the x direction. That's the direction we care about. So let me expand the linear momentum equation in the x direction. Again, our control volume is not accelerating. We have a fixed coordinate system, fixed control volume, so I don't have any acceleration term in my linear momentum equation to worry about. And we'll, again, just evaluate what each term is piece by piece. So let's figure out, this is the time rate of change of x linear momentum inside the control volume. Well, we said that we're dealing with a steady state, so nothing is changing. The ux velocity is not changing with time, the density is not changing with time, the volume is not changing with time, so this term is 0. Again, everything's just fixed with time, no variation with time. Let's go ahead and evaluate now. Let me do the second term. This is the linear momentum flow rate out of and into the control volume. That one's also pretty easy to figure out now as well, because we've said that the ux velocity is constant. So on the left-hand side here, the ux velocity is just ux. And the mass flow rate there, I'll just write as minus m dot. The mass flow rate here would be the density times the ux times the area, which would be dy times dz. And there'd be a negative in front of it because the flow is coming into the control volume. The velocity and the outward pointing normal vector are in opposite directions. So that's why I get the minus m dot. And then going out, still a ux velocity going out here. And then the mass flow rate out there will be the same mass flow rate, just from conservation of mass. Since there's no flow out through the top and bottom or the front and back, and it's steady, whatever comes in here has to be the same mass that goes out there. So it's the same m dot, but it's positive because the velocity vector and the outward pointing normal are in the same direction. So you can see that these two will add together to just be 0. So that one's easy as well. Let's go ahead and figure out the body force term in the x direction. Now, I didn't say it, I should have said it earlier, but I don't think I set it up here. One of our other assumptions for Couette flows, we're just going to assume no gravity in the x direction. So that would just be like g sub x is 0. We could relax that one, but just for the standard Couette flow, we usually don't worry about gravity. So in that case, there's no body force in the x direction. So that one goes to 0. So a lot of things are going to 0 here. The last one are the surface forces in the x direction. So in general, you might have, let's say, a pressure force here and a pressure force there. And you would have a shear stress on the top. I'm going to draw a positive shear stress on the top there, and then a positive shear stress on the bottom. Notice that when you have a shear stress on the bottom, this is what we call a negative face, and a positive shear stress on a negative face points in the negative direction. This is just the sign convention that's typically used for shear stresses. If you're unfamiliar with that, you need to go back and look through your strength of material notes. I won't go through it here for the sake of time. But hopefully you understand that. So we have some shear stresses on the top and bottom faces that act in the x direction. There could be shear stresses on the front and back faces, but since we have no flow variation in going in and out of the page, we won't develop any shear stresses because we need some sort of velocity gradient to develop the shear stresses. And if there's no flow variation between the front and the back, then there'll be no shear stresses to worry about. So these will be the only shear stresses we worry about there. So what we're going to do is this approach again where we say that the conditions at the center are like ux here. Let me erase that for clarity. We're going to say that the pressure at the center is just P. And I'll say that the shear stress that's of interest is just tau yx. It's on a y face in the x direction. Again, if you're uncertain about the notation for shear stresses, go back and look at some strength of material notes and you'll see how it's defined there. So we're going to say that the pressure and the shear stress at the center are that, so that the pressure on the right-hand side will be P plus dp dx times dx over 2. And the pressure on the left will be P plus dp dx times minus dx over 2. Right? We're doing this game again where we say the pressure is P at the center, and then we see how the pressure varies in the x direction as we go from the center to the right, times how far we've moved to get there. And then we do the same thing as we go left, but as we go left, we're going a distance of minus dx over 2. We can do the same thing for the shear stresses on the top and bottom. On the top, it'll be tau yx plus d tau yx dy times how far we've moved, which would be dy over 2. And you can do the same on the bottom face, except there we've moved a distance of minus dy over 2. So I can now start writing out what my surface forces are in terms of the pressure and shear stresses. Now let me simplify things a little bit here. We said that there was no pressure gradient in the x direction. There are different ways you can move fluid. three different ways, basically. One way to move fluid is through a moving boundary, like what we have here for the Couette flow. As we move the boundary, it drags the fluid with it. A second way you can move fluid is with a pressure gradient. So if you push on one side of the fluid, let's say the pressure here was larger than the pressure there, then we'd get the fluid moving from left to right. So a pressure gradient, if the pressure varies in the x direction, the fluid will be pushed along. So in this particular problem, this Couette flow, we're saying there is no pressure gradient driving it. And then the third way you can move fluid is through gravity. If you tilt the surface, for example, so that gravity's acting to pull the fluid downward, then it would start to move. Again, in a standard Couette flow, we say that there's no movement due to gravity. So the fluid in a Couette flow is moved only by the boundary, not by pressure or by gravity. So in that case, I'm just going to say the pressure gradient is 0. So assumed no dp dx. That was just one of our assumptions that we made. And so the only surface force we have is really the shear stress terms. So let me write those out. We'll do the one on the top first. So that's going to be tau yx plus d tau yx times dy over 2. And then the area that this shear stress is acting on is this area right here. That'll be dx times dz. And then we have the same sort of thing on the bottom, except now here it's acting, the shear stress is acting toward the left. So I'm going to have a minus tau yx plus d tau yx dy times a minus dy over 2. It's acting on the same area, dx times dz. And that's all we have for the surface force terms. And if you look at that, we can simplify it. That tau and that tau will cancel out, and then the d tau dy terms will actually add together, because this top one is positive and the bottom one has two negatives that make it positive. So this will just end up becoming d tau yx times dy times dx dy dz. All right, so now we can substitute everything back into the linear momentum equation. So the first term here is just 0. The second term is also 0. The body force term is 0. The only thing we have is the surface force term, which is this. So we'll substitute and simplify. Okay, so that's what we have when we substitute back into the linear momentum equation. In general, dx dy dz is not 0, so we can divide through by that. So really all we're left with is that the shear stress does not vary in the y direction. That's what that tells us. Now let's think about this for a moment. In this particular flow field, actually let me go back for a second. The expression that I derived here is true whether or not the flow is like Newtonian or non-Newtonian. There's nothing that I did in this derivation that said that the flow was Newtonian or non-Newtonian. So this is actually true for non-Newtonian fluids as well as Newtonian fluids. I'm going to say at this point we're going to make another assumption that we're dealing with a Newtonian fluid. So let me mark that down up here as well. I didn't say that earlier, but I'm going to say it now. So we're going to assume that we're dealing with a Newtonian fluid. And when I do that, what that means is that the shear stress can now be written in terms of the velocity gradient in a known way. So Newtonian just means that the tau yx stress looks like this. Oops, fix that. This is the most general form of what the shear stress looks like for a Newtonian fluid. Keep in mind that we said that the y velocity is 0 everywhere, plus it doesn't vary in the x direction anyway, so that term is just 0. So what we're left with is tau yx is just dux dy times the viscosity. So we can substitute that in back up into here, and so now we're going to have d dy of mu times dux dy is equal to 0. And then in general, we're just going to say, we'll assume that we have a constant I shouldn't say in general, we're just going to assume that we have a constant dynamic viscosity so we can pull it outside the derivative, and so then what we'll be left with is this differential equation. Okay? In general, the viscosity is not zero, so then we can write it simply as this. So now what we have is a differential equation for the x velocity. Remember, the whole point of this exercise is to derive what the velocity looks like in the x direction. So we're almost there. We have a differential equation that we need to solve. At this point, I'm going to do something a little mathematical. It's just a notational effect. If you'll notice that I've got a set of partial derivatives here. We can actually write those as ordinary derivatives. And the reason we can do that is, think again over here. The ux velocity in general could be a function of time, x, y, and z, right? But we said that the flow is steady, so it's not going to be a function of time. We said the flow is fully developed in the x direction, so it's not going to vary in the x direction. And we said the flow is planar, so it's not going to vary in the z direction either. So at most, what we're going to have is the x velocity could be a function of y. So that means that these partial derivatives just become ordinary derivatives. It's just a little mathematical notation just to let you know that actually the x velocity is only a function of y. This turns out to be a pretty simple differential equation to solve. You can integrate it once. Look at this, C1 is an unknown constant, and then we can integrate it one more time and we'll get a second unknown constant. So that's what our velocity profile will look like in this Couette flow. C1 and C2 are unknown constants. We have to find those. But in general, you can see this looks like a linear profile, right? A straight line. Now to find what the C1 and C2 are, we need to use boundary conditions. So our boundary conditions here will be, let me go back up to the picture. There'll be the no-slip boundary condition at the bottom wall and the no-slip condition at the top wall. So let's go ahead and write those down. I like to write boundary conditions in words first and then in mathematics. So at the bottom wall, the ux at y is equal to 0 is 0. And what that'll tell you pretty quickly is that C2 comes out to be 0. And then we have no slip at the top wall. So that's ux at y is equal to h is equal to capital U, right? And so that'll tell us that C1 will end up being, let me think about that, C1 will be capital U over h. So then our velocity profile will now look like capital U times y over h. So that is now our velocity profile. So if I sketch it out, here we have the top wall moving at capital U velocity, bottom wall is fixed. And our velocity profile will be linear. It'll look like that. Just keeping in mind that the y component is acting upward here and that these are separated by distance capital H. So earlier in the course, we gave you a linear velocity profile for a Couette flow, but now here what we did is we actually derived it. And we derived it using conservation of mass and the linear momentum equation just applied to a tiny little control volume. We can do this same sort of approach for many different geometries. So for example, in this case, let me go back up here. I assumed that I was dealing with, let's say, no pressure gradient. Well, I could actually relax that. I could give a fixed pressure gradient, and if I did that, then what would happen is I would now have pressure force terms that would show up in the surface force. But I could account for that. I could include that in there. If I knew what the pressure gradient was, then I would have an extra term in here that would have a pressure gradient. So we could relax that one as well. And that's called a Couette-Poiseuille flow. It's when you drive the flow with a moving boundary as well as with a pressure gradient. I could have also dealt with a non-Newtonian fluid. The way I would handle that is when I got back down to this, I would have a different expression for how the shear stress and velocity gradient are related. So I would need to know what that relationship is, but once I know it, I could then write my shear stress in terms of this other kind of relationship with the velocity gradient, plug it back in here, and then solve the differential equation. So I could handle a non-Newtonian fluid. I could also deal with gravity, for example. If I had gravity, then what would happen is my body force term would no longer be zero, and so I would have that expression in here. But you can handle those sorts of things. So this approach is very general, and it's just using small control volumes along with conservation of mass and linear momentum. Once you know the velocity profile down here, then you can find all kinds of other things. So for example, if I wanted to find the shear stress anywhere, I could just simply, of course, take the partial derivative. Again, this is just only a function of y, so it would look like this. I could just take the derivative. This would just end up giving me the following for the shear stress acting on any bit of fluid. You can see in this particular case, it's a constant shear stress. So that's the shear stress exerted on a fluid element. I could find a mass, I could find a volumetric flow rate. Imagine we have an area here and you wanted to find the volumetric flow rate through that. Now that we have the velocity profile, we could easily find it. So the volumetric flow rate will be the x velocity times the little bit of area that the velocity is passing through. That'd be like dy. dy is just a little displacement this way. And then times the distance in and out of the page, I'll just call that w for the time being. And then we integrate that as y goes from 0 to h. So we could find the volumetric flow rate that way. So once you have the velocity profile, you can find many other things. Okay, I think we'll go ahead and end the video lecture there. Hopefully you understand how to use these differential control volumes. They're very flexible. You can use them in a variety of different geometries. And again, the whole idea here is you're trying to derive a velocity profile. Okay, so we'll end it there.